Okay, here's a video that continues the discussion from section 4.5 of the text, and this is about multimode distortion. I just got done talking about waveguide dispersion, okay, and it turns out that for multimode fibers there's yet another contributing factor to the total pulse spreading per unit length. We don't call this a dispersion, though, because it is not a wavelength dependent thing. There's no delta lambda involved in this, in the equation that we're going to arrive at. And really, you can think of it in terms of the multimode fiber. If this is a multimode fiber, I abbreviate multimode by MM, or a multimode or fiber or waveguide. It'll support multiple modes, and each mode can be characterized by a particular zigzag angle through the fiber. Okay, so there's one mode. Here's another mode. Okay, so multiple modes are supported. And each one has a different effective index, okay, and we know that from our mode plot, where N effective ranges from N2 to N1, d by lambda starts at 0, and we have our mode plot, maybe something like this. And if, for example, our waveguide thickness d is, suppose d by lambda is equal to this value, then we've got two modes, each with different N effectives. Okay? And so each mode has a different propagation speed due to a different N effective value. So we have N effective number 0 for mode 0, and N effective 1 for mode 1, let's say. And so the propagation speed varies with the mode number. And what that means is that even without a delta lambda, even if we did have perfectly monochromatic light somehow in these, occupying these modes, they would go at different speeds. So it turns out that to calculate the pulse spreading, in this case, all we have to do is consider calculating the differential arrival time. Okay, and that's in contrast to the dispersive effects, where we can't just take the slope of the N effective plot, for example, taking two different wavelengths separated by delta lambda and calculating the difference in N effective and then going and calculating the difference in arrival time based on that. That doesn't work for the dispersive one, and in fact is proportional to the second derivative of N by lambda rather than that first derivative. But here it's a simpler situation. And so delta tau is easy to calculate based on differential arrival times. Of the modes. So as you launch multiple modes into the fiber, at the other end of the fiber they're going to arrive at different times, and that causes pulse spreading. Okay, so the pulse may be evenly divided between two modes here, in which case the energy that arrives due to that pulse comes in two pulses at the other end of the fiber. And of course it's also proportional to the distance traveled, so it is a pulse spreading that's proportional to the distance traveled, so it's going to be pulse spreading per unit length. And so delta tau is equal to delta arrival time. And that's easy to write down. It's equal to delta n over c. Okay, let's see, the speed is and then times L. Okay, so this is the difference in the arrival times when I have two n's, where delta n is equal to n effective 0 minus n effective 1 in this case. Where here I've taken the case where I've got only two modes propagating. And so my delta tau arises because of the difference between those two effective indices. More typical in multimode fibers, you're going to have many modes, maybe dozens of modes propagating, in which case you would take the difference between the highest effective index and the lowest effective index for the fiber. So this should really be, what I'll do is I'll just notate here for more than two modes, use the total range of n effectives present in the fiber. Okay, and so if I have enough room over here, what we'll do is we'll write down that delta tau, and now I'm going to go ahead and divide by L. So delta tau over L is delta n over c, which can be written as n1 delta all over c. Now this is kind of tricky because we use delta in several different ways here, and this is following the notation in the book, and this is standard notation, believe it or not. We write delta n to mean the difference between two effective index values. We write a delta on the outside of a parenthesis to mean the change in the arrival time, but we also have a delta defined for our waveguide. And I don't think I've done any of the math associated with that. I'll show you a quick little derivation that's pretty useful. Well, first of all, I'll finish up this equation. And this equation, if I can find it, this equation is also equal to, approximately equal to, the numerical aperture squared all over 2c n1. Okay, so this is what is called the modal dispersion per unit, multimode distortion. And so I'll put a MOD subscript on that quantity. Okay. I'll come back to the definition of delta. Well, I'll give you the definition of delta right here. Delta is n1 minus n2 over n1. And this characterizes our waveguide. Okay, so we have the core and the cladding indices. Okay, so we can rewrite this delta n over c in a couple of different ways. And sometimes it's useful to have the modal dispersion written in terms of the numerical aperture. Okay, and so finally, the total pulse spreading, or the total pulse spreading is due to both dispersive and modal effects. And I'll go ahead and keep this separated. Hope it's not too confusing to have it all overlapping. Total. Now it turns out that we can't just add our two contributions. We've got modal pulse spreading and we've got dispersive pulse spreading per unit length. In the dispersive one, we were able to add the material and the waveguide dispersion quantities, and that gave us our total pulse spread per unit length due to dispersive effects. But here we have to add them in the squared sense because they act as if they're orthogonal vectors. And in any case, there's no telling whether or not they will add constructively or destructively in some sense. And so we're going to write delta tau by L dispersive plus delta tau by L modal. Okay, and maybe I'll make my square root go all the way around. I ran out of room, sorry. In any case, it's the sum of these two squared. And then you take the square root of that. Okay, so they add in the squared sense, kind of like the Pythagorean theorem. And that means that there's no telling whether they're going to add up or cancel each other out in general. Okay, let me show you a very quick little derivation here that may be of use to you in your homework problems. We call the waveguide index delta. Delta is n1 minus n2 all over n1. So this is the relative refractive index difference. Okay, so this is the relative delta. And we can put NA in terms of delta. We can write that N2 is equal to N1 minus N1 times delta. And we can therefore write that N2 squared is this thing squared, which comes to be N1 squared, 1 minus 2 delta plus delta squared. But if delta is small, then we can say that this is approximately equal to N1 squared minus 2 delta N1 squared. In other words, N2 squared minus N1 squared is approximately equal to, N1 squared minus N2 squared is approximately equal to 2 delta N1 squared. In other words, the numerical aperture, which we know is equal to the square root of N1 squared minus N2 squared for our slab waveguide. And so the numerical aperture can also be written as approximately equal to N1, let's see here, N1 squared minus N2 squared, so the square root of this, and this is a delta times N1, not delta N1. So the square root of this is N1 times the square root of 2 delta. Okay, I think this is useful in at least one of your homework problems. And this is, this delta is called the relative refractive index difference. Okay, I'll stop here. Thanks.